Good morning, guys. I got a really interesting email the other day saying, look, I understand how to integrate something, I understand how to write the answer, but I still don't actually know what it means and I don't know where it came from. So I thought that's a fantastic opportunity for me because, it's a great question. It's a question showing a thirst for understanding. When you get to the more challenging questions, having understanding about why something happens will certainly be of advantage to you. So, where does integration come from? Well, it comes from the study of exact areas. Okay, and you might think, well, how does that work? Exact areas. Okay, we can certainly find exact areas of objects like circles. Okay, using pi r squared, keeping pi as pi. We can find exact areas of right-angled triangles, half base times height. The most basic of areas that we can find, if you think about what you very first learned probably back in primary school, is the areas of a rectangle. For example, let's call it height times width, or base times height, or whatever you want to call it, length times breadth. And I guess if we're talking about different families of shapes, they're the three main families. I know quadrilaterals, yes, you can find squares, trapeziums, parallelograms, kites, rhombuses, all that sort of stuff, but different objects, certainly they would be your three that you'd be looking at. And then, of course, as mathematicians, we question things. So people said, well, what about, a parabola? What about an exponential curve? It's not really looking like an exponential curve, is it? An exponential curve. What about, graphs that we have no idea, or not an idea, but have really weird functions? What about finding the areas underneath those particular lines? So sort of curved lines. How can we find the area of those things? Well, people said, well, why would you want to find areas underneath those things? For what benefit would it have to us? And I guess as mathematicians, our answer to that is, well, the fact is not what we can use it for, but it's the fact that we can't do it. Life is full of challenges. Life is full of having things that we're told we can't do. You can't find the value of that. And they say, well, you know what? I want to. I want to find the exact value of it because currently we're not able to. And I guess, so why have I chosen those two particular graphs? I could have chosen any graphs, but I chose those two to start off with because, this is to do with motion, I guess, motion and gravity, which is something we look at in this unit. Or this course. What goes up must come down. Look at exponential growth and decay. Obviously that would be growth because it's increasing, decay will be decreasing, which is looking at populations. And certainly, that information might help us in the long term. But at the moment, we just want to be able to find the area, the exact area underneath those curves. Now, yes, we can find estimations for it. We've got people who came up with, like the Simpsons rule, that used it into the rectangles and said, I'm going to find an approximate area of. Remembering that, we're going to be missing those little extra bits in there. We had the trapezoidal rule, which broke it up into, trapeziums, which again, was a different way to find a different approximation of the area underneath those curves. Obviously between 2 points, because you've got to have a starting point and an ending point, otherwise it's infinite, I guess. But those dealt with approximations. They don't deal with exact. Okay, so that's what the whole idea of integration was, is I want to find the exact area underneath those curves. And a lot of people worked towards this and probably had a lot of influence on it, but one of the main, I guess, fathers of integration was a guy called Reinhard Riemann. Now, he was a German mathematician in the 1800s. He, around the 1850s somewhere, really delved into this. And he was to do with algebra and geometry. And geometry, it's to do with shapes and areas. And so he really took it upon himself and said, this is something that I want to find out. So, if we look at the exponential curve, he said, okay, let's say we have a starting point of A and B. And he goes, I want to find the area underneath that curve. I don't want to use the estimation methods because I want to find an exact part of it. So his theory came from, well, what do we know so far? What have people been able to do? Okay, and he sort of said, okay, well, people have been able to find approximation. So we've been using rectangles like that, which will give us an approximate value of. And so, well, what if we broke these rectangles up into smaller rectangles? Because the smaller these rectangles are, then the less bits we are missing. Okay, I guess if you relate it back to pi, when we're trying to find the circumference of pi, or the area of pi, should I say, we cut this up into really little bit smalls of triangles, and we put it together to make that rectangle. Okay, I guess in one respect it's the same sort of theory, that I'm going to split this up into really infinitesimally small sort of widths of rectangles, that those little tiny bits are going to be so small that they're going to be nothing. They're going to have no bearing at all, and I'm going to be left with an exact area. So we said, okay, well, let's find a definition for the area to start off with of one of those rectangles. Okay, well, we know that the area of a rectangle is width times height. Okay, so let's talk about, if this is the function y equals f of x, then the height of one of those rectangles will be that y value, won't it? Because that's the height, is y, which is f of x. So my height will be f of x times the width, well, let's call that w. And that's of one rectangle. So we've got all these infinitesimally small rectangles. And so I'm going to add all these up. So let's do the sum of, okay, the sigma sign, which means the sum of. And let's say as w equals a, okay, because this is my width, that starts at a and we end in b. So we sort of came up with this whole idea and said, well, okay, well, we needed a better idea of w, because w isn't just w. We want it so infinitesimally small that it's not going to be nearly zero. Obviously, it can't be zero because then it wouldn't exist, but it's going to be so small that it's going to be nearly zero. Now, where have we looked at that concept before? Apart from obviously looking at the circles, we looked at it this year. And let's go back to finding, I guess, gradients. We had a curve earlier on this year, and I said, okay, I want you to find the gradient at that particular point. And we said, okay, well, the gradient would be of a tangent at that point. But the problem is I only have 1 point. I can't find the gradient at that 1 point. So we had to go ahead and we had to take 2 points on the curve as such. And then we used the rise over the run, or my rise is my y value, my run is the x value. And then what we then did, once we found the gradient of that part, we then took a point which was closer to it. And another point, again, that was even closer still. To a point where we kept getting so small, where I guess we spoke that h approached 0, that it wasn't actually 0, but it was so close to 0 that that became our gradient of that point. Now, we said the gradient was rise over run, so we use a symbol, not y, we said dy, which means infinitesimally small y values, and dx, which means infinitesimally small x values. So we said, okay, well, rise equals, so our gradient equals rise over run, and if our rise is the infinitesimally small y values, dy, and infinitesimally small x values, dx, then the gradient equals dy dx. So we came up with that symbol, and that's the whole idea of differentiation of gradient is dy dx. So that's that infinitesimally small y values, infinitesimally small x values. So we're going to use the same thing. Said, okay, well, this is my x-axis, I guess. Well, I've used w here, but if it's my x-axis, then what we're going to do, we're going to replace this w, and we're going to replace it with dx. So that's my height is fx, is how high it goes up. And my dx is the infinitesimally small widths of those rectangles. So I said, okay, that's a better expression. Except the problem is sigma had already been used at that stage. And so we had to come up with a new symbol for sum of. Now, obviously, S was that's why they used sigma, because S meant speed. So what can we use for a symbol? So he went for a very big S, okay, which is our, or what you call integral, our integral sign now. It's our our S signs, the sum of our height times the width, so fx dx, from the point A to the point B, because obviously you need to have a starting point and a finishing point. And that has led to, or was the birth of, integration. Now he, of course, called it Riemann's integral, but yeah, it's a birth of the fundamental theorem of calculus. He didn't really know what he was finding. He just knew that he was trying to find the area underneath the curve. He didn't actually know what it was going to, end up being used for. So what we're going to do, we're going to apply that to a real life situation. So we're going to give well, not a real life situation, but an example. So I'm going to give a graph. I'm going to use an easier graph because, makes it easier for us to sort of look at. We're going to call that the point, let's say 2, and that point there is 6, and that point there is 8. So that point is going to be the coordinate 8, 6. And we've got the coordinate 0, 2. Okay. So what we're going to do is I'm going to ask you to find the gradient of that straight line. That's a little bit easier for us. So hopefully you remember the gradient of a straight line is rise over run. So in this case, the rise will be 6 take away 2, how far up that triangle goes from those two coordinates. And then the run would be between 8 and 0, so 8 take away 0. Which 6 take away 2 is 4, so 4 over 8 is a half. So the gradient of that straight line is a half. Now with that, we can come up with the rule for this line, or the function name. Y is equal to a half x plus 2. But what does that sort of gradient tell us? What does this a half represent for us? Now, what can we do with it? You've learnt so far in this course how to sketch the gradient function. That's something we can do, isn't it? Well, if the gradient is a half, let's put a half there. That could be 1. We could sketch the line a half, which would be a constant gradient. I can still put my 8 in there as well, which means at any of those points, the gradient is always the same, which makes sense because the gradient is a straight line. It doesn't change. It's not like a curve where it gets steeper or gets shallower, or it's increasing or decreasing. It's just one constant line. So that shows us, our gradient function. What else does it show us? Well, we use that word constant. And when we talk about constant, I guess we talk about speed. And that's great because when we talk about the gradient, which we know gradient is rate of change, as one thing changes, something else changes. In this case, we could talk about distance and time, how far something goes in a certain amount of time, which is what speed is. Speed is how far you go divided by the time. Distance equals speed over time. This would work in really nicely with speed because the gradient function is speed. And I guess, if we looked at a question like this, we've got the gradient of a half, or speed, a speed of a half, I guess, and 8. We could say that, if we're looking to find the distance, for example, from that question, distance would be found by doing speed times time. And if I know we've gone a half, and our time is 8 seconds, that we know we've gone 4 units per second. Okay, so that's found as something useful. And I guess that's a real life application of gradient in action. Okay, we can use this to find speed, distance, time, and all sorts of things with that. But that 4, I want to look at that because that's quite interesting. Because think about, if that height is a half and that length is 8, then a half of 8, or a half times 8, is actually 4. So what has happened, I've found the area of that rectangle, which is the same as that 4. So 4 units per second. Now, if I look at the very first example, okay, which is, I guess, if we relate it back, if this is our second example, this is y dash, and this is y, going backwards, this would be called our primitive function, wouldn't it? Our primitive function, or our antiderivative. I use that word as well. That 4 is, I said, is the distance, isn't it? And you look at this distance here, because that's on my y-axis, is the distance between 6 and 2, which is 4, which is really kind of cool, because that area underneath there, that area underneath that curve there, is the same as finding the difference of those two y values of the primitive function. And this is where they stumbled upon this great fundamental theorem of calculus, that the area underneath a curve has a direct relationship with the primitive function. I'm hoping you're starting to see some connections there. Okay. Now, I'm just going to remove this for a moment. If we look at it in one sense, I guess this is what they come. They said if I want to find the area, now remember we use the area, okay, as the integral sign, f of x dx, which means the height times the width between A and B. We said if we can find the antiderivative, and let's say if we got f of x is our function, we're going to call our primitive function capital F. If I can find out what these two values are here, then all I need to do is subtract those two values. Now, how do I find those two values? Well, we can find the top one, which is over here, by substituting that A into it, which I guess if we call this A and B like we did before, we can call that B. So, if I chuck in f of 8, that would give me, that's the function, which we'll do here. The function of f of 8, well, a half of 8 is 4, 4 plus 2 is 6, take away. And then if I take away the function of f of A, so A in this case was 0, so let's put 0 into this function. Half times 0 is 0 plus 2 is 2. The answer is 4. And that's a really cool concept. So the whole idea of fundamental theorem of calculus, it came from trying to find the area underneath the curve, but then seeing the relationship between that and its primitive function. And that is what integration is all about. Okay, we're going to apply it to, I guess, a proper question that you might get. So they might ask you to find the area under the curve. It doesn't even look like curve. Y equals, let's say, 3x squared plus 1. Actually, I'll just do 3x squared. Don't need to make it any more challenging than what it needs to be. So 3x squared between the values, let's say x equals 0 and x equals 4. And often we say and bound by the x-axis. That's often what it says, because what it's asking you to do, I guess we're getting a parabola, 3x squared between 0 and 4, like that, and asking you to find the area bound between those 2 points and the x-axis. So what we've just come up with is saying, well, if I want to find the area, okay, between these points, so remember we said the function, so 3x squared times dx, which is the width, that infinitesimally small, between 0 and 4, what that's the same as doing is finding the primitive function and subbing in the b value and then subbing in the a value and subtracting them. So that primitive function we know, in this case, the rule was we add 1 to the indice and then divide by the indice plus c. That was our primitive function. The 3's will cancel out, so we get x cubed plus c. Now, the only issue is that plus c, we know, is a value we don't know what it's going to be. It could be plus 10, could be plus a million, could be minus something. We don't know what it's going to be. Does it matter? Well, we'll see. So now let's substitute in these values 0 and 4, like we've said here. So if I put 4 in, well, 4 cubed is 64 plus c. That's the first value. Minus, if I sub in 0, well, 0 cubed is 0 plus c. So we get 64 plus c minus 0 minus c. Well, c minus c cancels out, so we're left just with 64 units squared. And the good thing is that plus c, that's going to cancel out every single time. So in fact, we don't even need to put that plus c. Now, how I write this, coming from that part of the question, is we often put square brackets and we put the integral inside there of x cubed, and then I put my a and b like we have up here. We just put them over here. Okay, and it's a simple matter of doing f of b take away f of a, which is the integral of and sub in b, so 4 cubed minus 0 cubed, which gives me the answer of 64 units squared. And that, my friends, is the fundamental theorem of calculus, to find the area underneath a curve. That is what integration is. That is where it came from. Now, the good thing is what you really need to know is just how to do it, but obviously having the understanding about, where the dx came from. Remember that, our f of x is the height of the rectangles, the dx is the infinitesimally small width of the triangles, and that's the area. And then we add the sum of them together between the 2 points A and B. That's where it all comes from. Look, I hope this made a bit of sense to you, and I hope it cleared up the idea of where it came from. As I said, it does give you a bit of understanding, and it does certainly help you with those harder questions. But certainly, if you try to improve your understanding of it, have a look on YouTube. There are thousands of videos about finding the area underneath a curve and how integration sort of came about. And certainly, my reasoning and my answers are probably very basic compared to what they are. But if you have a thirst for that knowledge, guys, that understanding, please go ahead and do a bit of research, because it is quite interesting. Have a great day, guys. I hope this was useful to you.